All right, guys, Mr. Antonucci here, and in this video, we're going to look at our second learning objective, solve differential equations involving what's called uninhibited growth and decay. Now, these equations show up in a lot of situations that involve science, nature, economics, radioactive decay, population growth, interest, um, and those kind of things. So this equation, dA dt equals Ka, basically says that the rate of change of A with respect to T is directly proportional to A itself. Now, if the number in front of K is positive, then this rate of change will also be positive, and the amount A is going to be increasing. This is what we call a growth model. If K is less than zero, then the rate of change is going to be negative and the amount of A is going to be decreasing, and therefore it's going to be a decay model. So I want to just run through how to solve this differential equation with you really quickly. So um, dA dt equals K dt. Notice, first of all, this is a separable differential equation. Oops, I accidentally, this should have been Ka. Okay, so divide by A equals K dt. And then the next thing we're going to do is integrate both sides. So let me rewrite it over here. You would have the integral of dA over A equals the integral of K dt. All right, so this is basically the antiderivative of the natural with the natural log. So natural log absolute value of A equals the antiderivative of K with respect to T. Remember, K is a constant, so this is going to be KT plus C. Now, since A is understood to be positive, I can take the absolute values off of the A, and this would be KT plus C. Okay, so the initial condition, so when T equals 0, then A is going to be, we'll just call it A naught. Okay, so if I substitute that in, natural log um, A equals KT plus natural log of A naught. All right. So then this would be, let me get some room here. We would have natural log of A minus natural log of A naught equals KT, and then natural log of A over A naught by the quotient property of logs is KT. And then we could exponentiate both sides because we're going to try to solve for A. All right. So you would have A over A naught equals e to the KT. And then if I solve for A, you would have A equals A naught e to the KT, where K is the constant of proportionality, A naught is the initial amount. Okay, so down here we just have our summary. The solution to the differential equation dA dt equals Ka is A equals A naught e to the KT, where A naught is the initial amount. So you have two situations, one where K is positive is going to result in exponential growth, and the other one where K is negative is going to result in exponential decay. And for all these situations, it's assumed that A is positive, okay? So let's move on here and actually look at an example. So assume a colony of bacteria grows at a rate proportional to the number of bacteria present. If the population of the colony doubles in 5 hours, how long does it take for the population of the colony to triple? So we're going to use N, capital N, to stand for the number of bacteria, and T for time. So since it's growing at a rate proportional to the number of bacteria present, this is a situation where you have like dn dt equals kn. All right. Now we just up here previously just solved that type of differential equation. So I know that the solution is going to be n of t equals the initial amount times e to the kt. Now, this one's a little different because you don't know the initial amount that it started with. But we do know that the population is going to double every 5 hours. So if if you plug 5 into the function, you should get twice whatever the initial amount is. Okay, so n of 5 is going to equal n naught e to the 5k, which should equal 2n naught. All right, so right here is where I plugged the 5 in for t, but I know also that it's going to double every 5 hours. So whatever the initial amount is, it's going to equal twice that initial amount. So I could divide both sides by the initial amount, and we would have e to the 5k equals 2. Then we could solve for k. Take the natural log of both sides. Then you have 5k equals natural log 2, and k equals natural log 2 over 5. Okay? So, or 1/5 natural log 2, however you want to write that. Now, we still don't know the initial amount present, but the question wants to know how long does it take for the initial amount to triple? So that's basically saying, well, when is n of t equal to 3 times the initial amount? All right, so n of t is n naught e to the kt. That's going to equal 3n naught. We can divide off the n naughts and get e to the kt equals 3. All right, and we could take the natural log of both sides. So natural log of e to the kt equals natural log of 3. So kt equals natural log of 3, and t equals natural log of 3 over k. We already solved for k over here, so it's natural log of 3 over natural log of 2 over 5. Now you're dividing by a fraction there, so you can multiply by the reciprocal, and we would have 5 times natural log of 3 over natural log of 2. Now, a couple things here. You can't write this as natural log of 3 minus 2 or cancel the natural log symbols. It's just 5 times the natural log of 3 over the natural log of 2. And if you dump that into your calculator or Desmos, you're going to get that that's about equal to 8. So it's going to take about 8 hours for the population to double. Okay? So another thing is that we have a situation with radioactive decay. We can use the equation dAdt equals kT. Another thing that often comes up is what's called the half-life of a radioactive substance. And the half-life is how long it takes for an amount to decay to half the original amount.